Hopefully by now everyone has been served. If you have not been served, make yourself known to the waitstaff. We are about to have our esteemed plenary speaker for this session come on up. But before we do that, I would like to ask, if at all possible, we abstain in terms of our excellent waitstaff and care we've been given from clearing tables while we have a speaker presenting, just to help with the noise. As we know, the acoustics in this room are phenomenal and they carry everything. So, yes, clapping as well. So with that said, we will do Q&A as we have for every other speaker. We will have runners at both ends of the room. So if you have some questions, hold them mentally. If you're like me, and I imagine a lot of other people, you may need to write them down because there's going to be a lot of great content. It might be hard to keep up and manage all those questions mentally. So with that as advice, it is my distinct honor to welcome Deke Arndt. Deke is the chief of the Climate Monitoring Branch at NOAA's National Centers for Environmental Information in Asheville, North Carolina. Thank you. NCEI is the largest archive of weather and climate data in the world. The monitoring group are the scorekeepers of the global climate system. They track climate on large scales, global warming, and on smaller scales such as regional drought, and they host the U.S. Drought Portal. Mr. Arndt has served as the lead or co-lead editor of the State of the Climate Report, the annual physical of the climate system published in the Bulletin of the American Meteorological Society since 2010. This year's version was written by 460 authors from 62 countries. You think managing your office is hard. Mr. Arndt is also the chair of the U.S. Global Change Research Program's Climate Indicator Working Group. He holds a bachelor's and master's degree in meteorology from the University of Oklahoma. As you can well imagine, the topic of his presentation is of high relevance to the work that we do, and I couldn't be more excited to bring up the stage. Let's welcome Deke with a warm Catholic Charities welcome.
All right. Thanks for having me. Can you hear? Oh, I guess so. It's good to be here. I want to first apologize for being underdressed. I had a nicely pressed white shirt and had a coffee incident this morning, so this was the tomorrow on the plane outfit. So I apologize. It is not out of a lack of respect for what you do. I think it'll be pretty obvious in a few minutes how much I respect and personally admire the work that you do. It's good to be here. Just a little bit about me before we start. This is a neat kind of universe folding over on itself experience for me. I worked with emergency managers at the state, county, local, tribal level for about 10 years. Back in Oklahoma, I ran a program and we worked to get weather data and training and working with emergency managers on how public safety personnel and operational meteorologists could do a better job of sharing weather information. Is one of my favorite jobs I've ever had. I'm also a practicing Catholic. I've come from St. Eugene Parish in Asheville. As far as we know, the first solar Catholic institution in North Carolina. So it's kind of fun to be talking climate and Catholic charities and emergency management, having experienced quite a bit of all of those in my lifetime. So thank you for having me here. I'm really glad to be here. And so what are we going to do today? We're going to talk about a little bit about kind of what's going on with the climate system. Kind of the two questions that we often get. Actually, let's just throw in three questions. Is how do we know the climate is changing? And then the follow-up question for that is almost always, well, how do we know humans are driving that change? And then the question that kind of wraps around both of those is, well, why does it matter? And you guys are on the front lines often of why does it matter. You see firsthand how big environmental changes, big forces can impact the lives of the vulnerable and even the lives of those who aren't particularly vulnerable. And that's the answer. And we'll walk through kind of bits and pieces of those three questions. And then I'd like to close with a story it involves people in my life, but it's really about you and the work that you do, and I'd like to share that with you. All right, so this is the commercial. You can tune out for the next 30 seconds if you'd like. I come from the National Centers for Environmental Information. It's where weather data goes to retire. So once the observations are taken and used by the forecasters, they end up on tape or on computer disk or on paper even sometimes in our institution. And so our role in the world is to protect this data that the American taxpayers already purchased through their use of equipment, and to make sure it's available for those that need it. So that used to be like weather and climate researchers, and now it's almost everybody. Weather and climate data is a big part of people's daily operations. So that's who we serve. And so the imagery here is all of the weather observations that went into this map that this gentleman is presenting are combined in with this 110, 120-year-old rain gauge observation that's from Nebraska, actually. So that all ends up in this building, this kind of stone and glass government building, and is available to extract and to apply to whatever your project is. All right, so that's the commercial. Well, it's a second commercial, sorry. This is my group, and our group is the monitoring branch. Like Zach said, our job is to do the play-by-play of the climate system. So we track things like drought, extreme events, the global temperature. So we provide kind of the play-by-play of what's going on with the climate system in numbers, a little bit in English, but mostly in statistics and numbers. And we have another group dedicated to tracking drought in the U.S. and broadly in North America. Wonderful people. We all picked a really weird decade to be a government climatologist. It's been a great experience, but I've really come to admire the people on this screen. If my kids grow up to be like any one of these people, I'll be thrilled. They go, it's been an interesting decade. I'll just put it that way. So just a run around these folks come from all over the U.S. and Puerto Rico and work to try to bring clarity to what we understand in the climate system. So while the important big shot scientists work on the dynamics and the physics and the understanding of the climate system, we're kind of the operational side of that. We crank the numbers and make sure that theory is reflecting itself in the real world, and write a lot of reports. Ultimately, at heart, we're bureaucrats, so we write a lot of reports. If you like to read climate reports, they're available right there. So, all right. If you know us, it's probably one of two things. Our billion-dollar disasters, we track those. Or this is the global temperature for the planet, and this comes from weather stations around the world, ships and buoys from around the world that have been collecting since about the early 1800s. There's enough data to make a good estimate of the global temperature starting in about 1880 or so, and that's where our data set goes back to. So if you're looking from left to right on this graphic, the leftmost dot, the red circle, is the year 1880. The rightmost red circle is 2017, the last complete year that we've had. And if the dot is above the black line, that means that year was warmer than the 20th century average. If the dot's below the black line, that year was cooler than the 20th century average. So you can see we are warming, obviously. The pink lines are just the average of the 10 years that make up that decade. So that's just kind of a 10-year running average. So yeah, it bounces up and down. It's not the case that every year on the globe is warmer than the last one. There is a lot of what we call natural variability, the bouncing up and down, but the long-term trend is definitely up, and it's up by about the amount that the folks would have predicted about 25 years ago when they first really started trying to quantify these things. 2016 so far is the warmest year on record. 2017 backed off of that a little bit, but we are kind of in the last few years in a new neighborhood as far as global temperature. Yeah, and then 2018 is about right here. So we'll probably finish this year as the fourth or fifth warmest year on record for the globe since 1880. And this is the graphic that we see a lot. Global temperature is important to track scientifically to see what's going on with the world, but honestly, it doesn't have a whole lot of relevance to what's going on in Langston County. So we do track a lot of other things, but I guess what we're going to do here is walk. So this is the main piece of evidence that we have that the world is warming, but it's certainly not the only one, and we'll get into that. Yeah, however, no one was ever found dead under a trace of global temperature, right? It's what it does to the weather that matters. It's what it does to the ocean that matters. It's the temperature itself, the global temperature is a great thing for scientists to kick around, but I guarantee you'll never show up at the site of a disaster or at the place where people need help armed with the knowledge that it's 1.4 degrees warmer on average than it was 30 years ago. It's what it does to the weather that makes a difference. And it's how we respond to that and prepare for that that's going to make a difference in how effective we are in helping the vulnerable, and even the people that aren't as vulnerable. So how do we know climate is changing? We're going to, I think, bounce through some resources. So if you are curious, share where almost all of this information comes from, and you can go explore those on your own if you're so minded to do that. So some of this, especially the global stuff, will come from that State of the Climate report. Dr. Jessica Blunden was one of the people in the little mugshot galley that we had for the monitoring branch. She's been leading this for 8 years now. I've been her number 2 for all of those years, and this is where all those green countries are the ones that are contributing authors to this report. And it is the annual physical of the climate system. It's the diagnostic, kind of in technical language. It's the big folder that we produce every year that says this piece of the climate system changed by this much. This other piece of the climate system changed by that much. And this is a document that we've been publishing now. This, I think, was our 27th version that came out. So that's where a lot of it comes from. A lot of it comes from the National Climate Assessment, which was this U.S. climate report that came out about a week ago. I think it was a week ago Friday. So that was came out the day after Thanksgiving. And this is a little more broad than that State of the Climate report. The State of the Climate report is just all diagnostics. It's just scientists and instruments puking up numbers into a book, right? This is more thoughtful, like here's really what's going on. This is written in much more accessible language. This is also authored by scientists across the country, but it's published in Asheville. So it comes, the technical support and kind of the layout and the documentation and the metadata all come out of our sister monitoring branch, or the group that work across the hall from us there. And they have 2 basic resources. One of these is hot off the presses here on the left, and that's the big full report in English, written for real people that kind of walk through topic by topic. Here's what we know, here's how we know it, and here is the trajectory of those things in the future. The word assessment in science means what do we know and how do we know it? And that's what the National Climate Assessment brings. Ironically, we're laying to rest former president today, George Herbert Walker Bush, was the person that commissioned this work, and it eventually became codified into law by Congress that every 4 years we have to take this assessment of the climate system. So in 1990, and during his presidency, he established the means by which we do this. We keep track of what's going on in the climate system. And despite all of the politics that have kind of wafted over the top of this since the 90s, his work, his vision kind of moves forward. We increasingly are indebted to his initiative to help establish this. 13 agencies put this together across the federal government. All right, the rest of the stuff, the kind of more real-time operational stuff, comes from our branch, our monthly and seasonal analyses that we publish. And these are available. I won't go into the details of what we do, but we try to track, what happened, how significant was that, is that part of a trend, is it counter to a trend? We'll be putting out a report on Friday for the month of November and the season of autumn, which in the meteorology world is September, October, and November. For reasons I won't get into, but we'll be putting out a report that basically said, here's where drought was, and here's how bad it was, and here's how it's changing. Here's where temperatures behaved this way or that way, and how that's changing. With a focus on kind of the history of Novembers and the history of autumns across the U.S. And that's kind of our main day job in my branch. Built by lots of partners across the country that are taking observations and sending them to that big weather data retirement home in Asheville. All right, so again, how do we know climate? So those are the sources. Now let's look at some indicators. So these are going to be kind of big picture indicators is the right word, indicators of climate change. This is kind of if we hadn't anticipated this already and we saw these things happening, they would say the climate is changing, the globe is warming, and there's all these other attendant changes as well. So we're going to walk through 6 or 7 of these. There are about 300 in that State of the Climate report, but most of them are pretty obscure and related to specific parts of the world. So these are typically kind of global scale changes that we're seeing. All right. Uh-oh. Oh, there we go. Yeah, there's surface temperature, so that we've already looked at that one. This is probably the easiest, or at least the most directly related indicator of change. We've seen close to 1.5 degrees of warming since the middle of the 20th century. About 100% of that is driven by human activity for kind of rationale that we'll get to in a minute. But this is the change that we've seen, again, averaged across the globe, averaged across all seasons since the middle 20th century. Okay, we already looked at 2018. This is what warmest on record looks like on a map. So this is that 2016 year, the dot that was the highest, basically blown up onto a map. And the map on the left shows how much warmer or cooler a place was versus its normal 1981 to 2010 average. And the map on the right is the same data, but it just shows how a place ranked in 2016 versus that place's own history, that grid box's own history. So if you look at the one on the right, working from left to right, these categories on the map, if a place has a dark blue dot, and there was one off the southern tip of South America, that means that was the coldest year that place had since we've been keeping records in the late 1800s. The next one in is the coldest 10%, which we call much colder than average. The next one in would be in the coldest third of history. And in the middle, the neutral tone there is near average. That's in the middle third of history. So if you see that color, that box landed in the middle of its history. and then upper third, upper 10%, and warmest on record. You can see kind of the pink scales dominate, but not every part of the world was warmest on record during the world's warmest year on record. There are still little blobs of blue running around. There's little things that happen. Weather's still a pretty random and exciting thing. But overall, when you average together kind of all of those observations around, these come together to make it the warmest year, make 2016 the warmest year on record. Does that make sense? And you can, if you want to, please jump in with question. I know we got a lot of people in here, and we were a little, but if you do have a pressing question, please ask it, because it's probably in someone else's head as well. All right. The rate of warming varies around the world too. So across the bottom, we see that the Arctic is warming much faster than the rest of the world, and that's because the snow and ice that have covered much of that region is retreating a little more during the warm season every year, and where you used to have nice reflective white stuff that would bounce the incoming sunlight right back into space, when that stuff goes away, you either have ground that absorbs the sunlight or ocean that absorbs the sunlight, and so that additional feedback mechanism is making the Arctic warm a lot faster than the rest of the planet. Basically, it's undergoing the same global temperature change as the rest of the planet, but in addition, it's losing this kind of protective white sheet that bounces sunlight away. And that additional factor is making the Arctic change a lot more. So you'll often hear the Arctic is a crucible of climate change, and this is why. It's because the snow and ice cover is retreating over time. This is how much the rate of change since the early 20th century, and this is in the last 30 years. A few things to pick out here. The rate is a little more in recent years, so we're warming faster in the last few decades than we were generally over the 20th century. Also, the northern parts of the northern hemisphere, particularly over land, is warming a lot faster than the rest of the world, and that's part of that Arctic amplification that we just talked about. As the snow retreats seasonally, it retreats a little earlier, it shows up a little later in Canada and Siberia and Northern Europe. That's increasing their rate of warming over time. All right. And this is around the country as well. So this is from this latest National Climate Assessment. One of the things, if you're from the Mid-South or the Deep South, you're not warming much at all over the last few decades in the long run. So if you hear folks in your region say, I don't believe all that stuff, it sure hasn't seemed like it warmed here, they're right. It hasn't warmed. So this is kind of famously called the warming hole in the United States. What we think is going on, but the science isn't to a point where we would put this in the assessment. So to get in the assessment's a very conservative document. You really have to have science run the gamut, the steeplechase of criticism and review. But what we think is the case, and what will likely be confirmed, or as much as science can confirm it, is that this is also an area that's getting a lot more summer precipitation. And so what we think is going on is, as the Gulf of Mexico warms, there's a lot more cloud and precipitation in the Deep South. And so the warming signal is kind of manifest in all of this water that's evaporating from the Gulf of Mexico and making its way into a warmer atmosphere. And it is dumping, and it truly is getting wetter in the South. So that's likely what's going on, but that's not something that scientists would defend to the death yet. So there's still a lot of review to be going on in there. You can see that most of the country is warming. We have this warming hole in the South. We also have this strange dichotomy that the summer is not warming as quickly as the winter for much of the U.S. And that is kind of universally true in a 3 out of 4, 2 out of 3, 3 out of 5 kind of way, is the warm seasons are not warming as fast as the cold seasons. So the cold seasons are warming faster than the warm seasons. The cold times of day are warming faster than the warm times of day. the colder places are warming faster than the warmer places. We're seeing disproportionate amount of the warming signal coming from the cold times of day, the cold seasons, and the cold, like high altitude type places. And this is representative of that. In the summer in the US, this is again associated with a lot more precipitation happening, likely from a lot more moisture coming off the Gulf of Mexico, because a warmer atmosphere can hold a lot more water vapor, and a warmer Gulf of Mexico can pump a lot more water vapor into that atmosphere. This lack of warming in the summer is likely not just associated with, but caused by the fact that we're getting a lot more precipitation in the eastern U.S. in the summer. Does that make sense? All right. This is jumping back to that original time series of the globe. And we mentioned that it kind of bounces up and down. So the global temperature since about 1950, it's basically been like riding on an escalator and jumping up and down while you're riding along that escalator, right? So the longer you're on the escalator, the higher you are. But the higher you jump at any given year, you may kind of stick out from your neighbors. And the thing that's driving almost all of that bouncing up and down is, and this will be funny if you were paying attention during the 90s because it got blamed for everything, El Nino. So El Nino is the cause of everything, it seems like, and it's certainly the cause of the jumping up and down. And so this is the same data that we looked at, except instead of 1880 on the left, it's 1980 on the left. And instead of annual or yearly values, these are monthly values. So there's a bar on the very left that's January of 1980, and then there's one that's February of 1980, and so on. And we've colored the bars based on whether there was an El Nino active at the time, or a La Nina active at the time, or a neutral between the two, La Nada, going on at the time. So, okay, all right. All right, it's working. Okay, so, yes, you bet. So the question was, what is El Nino and La Nina? So in the Pacific Ocean, the trade winds, you've heard of the trade winds, you might be familiar with the trade winds, tend to blow from east to west in the equatorial parts of the globe. And if this is east and this is west, typically the winds would blow from east to west, and it kind of piles up the warmest water over here in the western Pacific. In an El Nino, those winds relax. They become almost zero, and this warm water that's kind of naturally piled up over in the western Pacific kind of sloshes back because there's not as much wind blowing it to the west. And so there's a much bigger footprint of warm water. Does that make sense? So in La Nina, the exact opposite happens. Those winds strengthen, and it kind of compresses the warm water even more, and the physics of those winds blowing across the water bring up a lot of cold water over here. Here's South America, and that's Australia over there, right? So you get a lot more cold, you get a big pool of cold water in the eastern equatorial Pacific. So that does a lot of things to seasonal weather. So when there's a La Nina, the eastern U.S. tends to have colder, wetter winters. When there's an El Nino, we tend to see droughtier conditions in parts of the U.S., Australia, and it has all of these kind of regional and seasonal impacts. But for the global temperature, just the fact that an El Nino event, when those winds relax and that warm water at the surface kind of sloshes back and you get a much larger warm pool, it's just like putting a big heating pad underneath the atmosphere, right? It's a larger chunk of warm water sharing its warmth into the atmosphere. Does that make sense? And so you can see on the red months on those graphs, they tend to stand up higher than their neighbors. So the overall trend is still up, but the red months, the months that had this large reservoir of really warm water heating the atmosphere, they tend to be warmer than the months around them. El Nino has a temporary warming influence on global temperatures. Does that make sense? Yeah, you can see that, right? So that every one of these El Nino events tends to be warmer than the neighboring months. They tend to, on the big ones, the long-lasting ones, they tend to warm throughout the event. The exception being this one right here in the early 90s. There was a big volcano that screwed everything up and ruined our statistics for a long time. But we figured out that that was the volcano's fault and not El Nino's fault. And then La Nina is the opposite. That larger area of colder water relative to normal tends to cool the global temperature, and you can see those months kind of down below the neighboring months, and they tend to cool during the course of an El Nino event. Yeah, so the question was, how predictable is this? And El Nino and La Nina are coupled together. I think we may even have that as the El Nino Southern Oscillation Phenomenon, ENSO. Sorry, ugly. It actually, because it's so big, and it tends to happen, the complete cycle tends to take 2 to 4 or 5 years. It's big and slow, and things that are big and slow are much easier to predict than things that are small and fast. And so it is fairly predictable. You can kind of see it coming, getting the magnitude or how intense it's going to be or how long it's going to last. Those are still areas that we have a lot of work to do. We have a sister agency, the National Weather Service, that kind of does all of these predictions through the Climate Prediction Center in Silver Spring, Maryland. They're kind of the world's experts on this stuff. There are a bunch of these types of sloshing phenomena. There's dozens of them around the world. This one just happens to be the biggest and one of the slowest. And so it's the one that we've been able to pay more attention to, take more observations, and understand better. Thanks, a great question. All right. It comes from the Christ child. So the El Nino event, thanks for asking that. I would have forgotten that. So the El Nino event was first noticed as really, really crummy anchovy harvests off the coast of Peru when this cold upwelling water, it's really nutrient rich. And you get a lot of anchovies in a typical year, and especially in a La Nina year. You get this cold water with all these nutrients. You get the fish feeding like crazy. But in that El Nino year, all this warm water kind of sloshes back, and you get really nutrient poor waters, and the anchovy harvest is a disaster. It always happens around December, so El Nino is the Christ child. And then La Nina, this opposite thing, was kind of a cute opposite way. And then La Nada is an even more unofficial, cute way to say. So yeah, Peruvian fishermen named the phenomenon. Thanks. Okay, so this is self-preservation here. It's kind of a commercial, but it's more of a plea for understanding. These are multiple data sets, so we're not the only group in the world that tries to measure global temperature. There's a group at NASA that does this. There's a group at the Japanese Meteorological Agency, and there's a group at the Hadley Center in the United Kingdom that track this. And we all use slightly different data. We all kind of recombine it in different ways. We make different assumptions about what to do when there's a lot of missing data in a part of the world. And so our analyses end up a little different from year to year. So we're all kind of singing the same song, but hitting different notes along the way. This is important to have multiple groups examining this issue. It really helps reduce the uncertainty that we have and increases the confidence that we can know what's going on, and our quantification of that is close to accurate. Because other groups that are doing things in some ways we would consider better than us, in some ways we would consider they're still catching up to us, but all of these different groups can compare notes and say, you know what, we're not as aggressive into the North Pole. There's not a lot of data up there. We're very conservative. So we actually miss a lot of the warming in the Arctic. NASA, they have no problem. They will make a lot of assumptions about missing data in the Arctic, and you can see they're a little warmer recently. And they're probably closer to the truth, but doing this and looking over each other's shoulder and kind of competing with each other to get the best product really helps us serve the larger public by being better at our jobs. So it's not just one. For all of these that we're about to look at, they're all based on multiple data sets, multiple lenses, multiple assumptions, kind of coming together to point towards something that's clearly happening. This is the other I'm sorry, there's two self-preservation slides. You may have heard that we mess with the data, And we do. We fidget around with the data to correct for things like stations moving. So let's say the Colorado Springs station, I don't know if it happened here, but a typical scenario in the US is the station used to be downtown, then commercial aviation and the Second World War happened, and we built a lot of large airports way out in the country with longer runways, and the weather station followed the aviation out to the airport, and then the town kind of grew around the airport. Well, over time, that can affect the reading. So when it was downtown, it was probably reading a little warm. When it was way out in the country, it was definitely reading cool. And as the city kind of grew up around the airport, that's a warming influence. Cities are warmer than countryside. And so we account for this. We let the data account for this. So what we'll do is take, in this example, the Colorado Springs station and compare its behavior to the 10 or 12 stations that are still rural and basically see, okay, do we know when this breakpoint happened? And kind of correct for that. Does that make sense? So that's one of the things we do. That turns out to be fairly negligible in the global temperature trace. The biggest correction we make is for sea surface temperature. And this is where we've been kind of following the lead of the Brits. The Brits have had a navy for a few hundred years more than us. So they're better at dealing with meteorological data over the oceans. But what they've led and what we've followed on is correcting for the way ocean temperatures are taken. So the oceans are 70% of the planet, right? They're by far the thing you need to measure well to get the global temperature right. And what happened is before World War II, the way that you measured sea surface temperature was you sent somebody to the deck of a boat with a rope and a bucket. And he would throw the bucket over the side of the boat and pull the bucket up and stick a thermometer in the bucket, wait 3 minutes if he was honest, and take the temperature, right? And that's how you measured sea surface temperature. And that was the way they did it since, the Captain Cook days. In World War II, turns out being on the deck of a boat is not a real cool place to be. So a combination of there are lots of guns, even if you were on a merchant ship, but also the convoys were limited to really kind of rough waters. And so the compromise was, let's take the temperature of the ocean as it comes into the engine room. So basically there's plumbing where water comes in to cool the engines in these boats, and you'd stick the thermometer in that plumbing. Well, it turns out that the guy throwing over the boat method, there's a lot of evaporation that happens around that bucket as it comes up and you're waiting for the temperature to, and that's a cooling influence, right? It's like when you get out of the shower, even on a hot, dry day, you get cold. Whew! It's cold when you hop out. It's because there's evaporation is a cooling process. As that water evaporates away from your skin, it's cooling you down. Same thing with a bucket that you've thrown over the side of a ship and you pulled up in the atmosphere. These ships are moving, there's wind, and so the bucket method, it's a great inventive name, that's called the bucket method. The bucket method reads cooler than the engine room method. The engine room method, that water is approaching the temperature of the engine room as the water approaches the engine room, and that's a slightly warming process. So we correct for this. And this is the self-preservation piece. So you can see if the raw data spoke for, so these are 3 of the same data sets I just showed in the previous slide. And this light blue one is our raw data. This is if we didn't correct the data, we didn't correct the fact that all those buckets were reading a lot cooler than the methods that they would today. We would have measured the early 20th century as quite a bit cooler than our corrections. The bottom line being, once we correct for this, we actually reduce the rate of warming that is seen in the raw observations. And if you want to do a scientist a favor, the next time you hear that we fiddle with the data to make it warmer, we actually fiddle with the data and it makes it a lot cooler. The cooling trend went from something like this to something like this based on these corrections that we made, largely due with the sea surface temperature. That make sense? All right. Okay. Multiple indicators. So it's not just temperature. Again, global temperature is a good measure, but it's not super relevant to real people's lives. But the things that we would expect to be going up are going up. The sea surface temperature, the amount of heat in the top kilometer or so of the ocean, the amount of humidity in the atmosphere. The things that are frozen tend to be going down. You know, glaciers, the mass and extent of sea ice, the snow cover, you know, so frozen stuff is going away. We'll look at some of these. The stuff that we would expect to go up are going up. Again, these indicators all singing the song that the globe is warming, the surface of the globe is warming, but none of us can tell, even together, they're not telling us why. But it's very clear through all of these indicators that the globe is warming and the things that would happen in a warming world are happening. This is the Arctic temperature amplification. You can see the Arctic temperature going up quite a bit faster than this muted global temperature signal. Sea ice. So this is a few years old, this graphic, but the one on the left is the one we'll focus on. So in the Arctic, the sea ice expands over the cold season. So beginning in October through kind of reaching a peak footprint in March, there's an expansion. So March is the month that we choose to measure when was sea ice in the Arctic at its greatest extent. And so the black dots on that line are the March sea ice extent values since the late 1970s when we got good satellite observations. Sea ice retreats in the warm season, so to a minimum almost always in September. So September is the month we choose for that monthly value represents sea ice when it was the smallest for a year. And so you can see that both of those are decreasing. Looking at the black curve, that's the March, that's saying that the maximum footprint of sea ice is getting a little smaller each year. What the red line is showing is when sea ice retreats to its minimum every year, that retreat is getting much smaller. So again, it's not even throughout the year. The summer season sea ice, the retreat is much more rapid and deeper than the annual expansion into March. Sea ice is an important indicator. The graphic on the right shows a decrease in multi-year sea ice that's survived more than a year in the Arctic tends to be tougher, it's harder to melt, and more of that multi-year sea ice is going away. So we're getting a lot more of that March sea ice is one-year ice, it's first-year ice. It's, you can think of it as a little more delicate than the grizzled old 2 and 3 and 4 year ice. A question here people always ask is, why don't you have the Antarctic sea ice on kind of equal footing here? And it's a great question. The reason Arctic sea ice is a better indicator of long-term climate change is the Arctic is an ocean surrounded by land, right? So if you look down the North Pole, you'll see Eurasia, you'll see North America kind of ringing the Arctic Ocean. Antarctic, the South Pole's the opposite. It's a land continent surrounded by the Southern Ocean. And its sea ice tends to expand and contract almost completely every year. So it almost erases itself, the South Pole. It expands out from Antarctica, and because of the way the ocean currents work, it kind of retreats every year. So it kind of resets every year. So Antarctic sea ice is a great indicator of what's going on that year. Arctic sea ice, because it has this multi-year component to it, where ice lives longer than 1 year, is a better indicator for longer-term climate change. That's why you'll often see, we put them both on equal footing in our reports, but a lot of scientists will look at just the Arctic, and that's why, and that's a very valid reason. A couple more indicators of change. Again, none of these are saying why. They're just saying, yes, this warming is being realized in different parts of the world. Permafrost, so the permanently frozen soils in the colder parts of the world, happens to be Alaska, are warming. So this is temperature. These are just boreholes. So you drill a hole in the ice and you go measure the temperature with depth, and you find the depth at which the soil is frozen. These are showing two things. So glaciers are losing ice, and the permanently frozen ice under the ground is warming. And when that happens, there's three kinds of, permafrost means permanently frozen soil, right? So it's just soil that's frozen. There's three kinds of permafrost. There's permanently frozen soil, so at no time during the year does this stuff thaw. It's hard, frozen ice soil all year round. Then there's the opposite of that, it's thawed all year. And then there's active, which means in a typical year it will go from a frozen state to a thawed state following kind of a predictable seasonal cycle. And what we're seeing is the permanently frozen stuff is creeping up in temperature. Some of the active permafrost, the region, the zones of active permafrost are getting larger. So stuff that was previously frozen all year is now seeing a freeze-thaw cycle. And then the stuff that we're seeing, again, the stuff that had a few months in a frozen state is going away into permanently thawed. And where this matters is where we've laid infrastructure, oil pipes, pipelines, villages of Native Alaskans. A lot of these were built assuming permanently frozen soils. So what we're seeing a lot is the energy industry needing to go back and kind of retrofit pipelines to drive piers into permanently frozen soil to protect against this heaving. It's like when your yard freezes and thaws, you get this heaving process. With the Native Alaskan villages, what happens is soil that used to be permanently frozen but is now thawed part of the year is much more susceptible to wave action if they're on the coast, right? It's softer soil, it can get washed away by waves. And so these villages are seeing rapid erosion now. And we've relocated several Native Alaskan villages inland. And so that's not just kind of a disruption to daily life, it's a disruption to the harvesting of large sea mammals, which is part of their local economy. It also means you have to dig up your ancestors and move them inland with you. You're displaced from the ocean. It's more than an economic cost. There's cultural loss as well that goes along with that. And that's one consequence that we don't hear about a lot down here, but this is going on in certain parts of the Alaskan coast. Does that make sense? All right. This is beginning to beat a dead horse, so we'll just go fast. These are related. As the globe warms, we are seeing sea surface temperatures warming as well. We're seeing sea level go up. So this is driven by two things. As water warms, it expands. So as the seas warm, they're expanding, and that causes sea levels to go up. And then as the frozen ice that was on land, as the glaciers melt, and that water runs off into the ocean, that tends to raise sea levels. So sea levels rising is a combination of roughly equal this thermal expansion and this new water that's coming off from glaciers. And then this on the right, bottom right here, is a measure of upper ocean heat content. About 90 to 95% of the additional energy trapped by greenhouse gases actually goes into the ocean. So we're only seeing about 5% of it realized up here above the ocean. Most of that energy, the oceans are like the big savings account for all of this additional energy. And so what this is you take a slab about 700 meters thick and you determine basically the extra units of energy running around in that slab, that uppermost part of the ocean. So I think it's joules here, like petajoules or something like that. But think of it as calories or BTUs or some unit of energy. That's where a lot of this is going. Again, different data sets trying to measure the same thing in different ways, singing the same song but hitting different notes along the way. All right, all of those together in chorus and dozens of other indicators are all saying, you know what, the world is warming. But none of them, they're not saying why. So here's why. The next few slides will kind of, let us know why. So first of all, it's been theorized for about 150 years. So we've been expecting this. We've found out carbon dioxide, methane, and nitrous oxide trapped heat. This is in the 1800s. And then we figured out in the early 1900s, if we increase these things, in the atmosphere, we should warm, and then by the middle 20th century, we started trying to put numbers on that. So even if we set that aside, that expectation, here are the ways that we would know. So greenhouse gases, these are the three big greenhouse gases: carbon dioxide, methane, and nitrous oxide. This is kind of a difficult, I try to explain it, but we'd all be in the fetal position by the end of this. So that just measures the impact of these three plus other gases. So carbon dioxide is the greenhouse gas. It's the one we always talk about. But it turns out that methane and nitrous oxide are both more potent greenhouse gases. So pound for pound, a pound of methane is going to trap more heat than a pound of carbon dioxide. A pound of nitrous oxide is going to trap more heat than them as well. The reason carbon dioxide is the greenhouse gas, in spite of it not being as potent as these others, is there's a lot more of it. It's measured in parts per million instead of parts per billion, and it lasts a lot longer. So carbon dioxide, if you remember back to your chemistry class, it's a really stable gas. It's really carbon dioxide is really happy to be carbon dioxide, and chemically it's really hard to undo that, right? We pack food in carbon dioxide for that reason. It's a non-reactive gas. It lasts a long time as that gas. So where methane and nitrous oxide will last decades to 1 or 2 centuries, depending on kind of how much and where, carbon dioxide will last up several centuries, up to a millennium or more in the atmosphere, kind of before half of it breaks down. That's why carbon dioxide is the gas that is still the greenhouse gas, even though these other increasing gases are becoming a little more important. There's not as much of them, and they're much shorter lived in the atmosphere. Where does it come from? And I cannot see that far. So this is a trace of carbon dioxide going back 800,000 years. We were dragging, this is from Antarctica, like Vostok ice cores, bubbles trapped in ice in the Antarctic. So what happens, these people are really cool. This is our paleo branch in Boulder that does this, right up the road here. So each year there's about an inch or two of snow that will happen. Antarctica is really dry, so there's not a lot of snow. There'll be an inch or two over the course of a year. The next year, an inch or two will fall on top of that. The next year, an inch or two will fall on top of that. And there's a lot of air kind of between those snowflakes from year to year. As you start piling up snow on that, it compresses the snow from the last few years down and eventually smashes it into ice. But that air that was between the snowflakes gets preserved as bubbles in that ice. And so if you drill a core through that ice sheet, you're basically going back in time as you're going down. And you can bring it into the lab and extract those gases out of the bubbles and kind of give a good estimate of, it's like tree rings. You know, they do tree ring stuff. It's like tree rings but with ice, right? Anyway, so based on their studies and a lot of other studies, this was the pre-industrial carbon dioxide, so we bounced around 200 to 300 parts per million, and now we're up here at 400 in recent years. And the sources are generally, and they're broken down into more specific categories here, but most of it's driven by carbon dioxide, and the kind of top 4 culprits in order of human carbon dioxide is fossil fuel burning. So converting coal or oil or natural gas that's pulled out of the ground, burning that for energy, the carbon dioxide is released into the atmosphere. That's the number 1. Deforestation is the number 2 contributor, and that's very much in the tropics. So forests, trees, vegetative matter, the way they grow is by pulling carbon dioxide out of the atmosphere and making leaves and branches. And so as you remove swaths of forest, you're reducing the capacity of it to pull carbon dioxide out of the atmosphere. That's the number 2 contributor. The number 3 contributor is agriculture, and it tends to be in more exotic gases, methane and nitrous oxide. And the number 4 contributor is concrete production and curation. So concrete cement is based on calcium carbonate. The carbon in carbonate, when it reacts and solidifies, it releases a lot of carbon dioxide. So those are the kind of four contributors to the increased greenhouse gases. So this is one way we know it, bringing that knowledge that we talked about, that 19th century and early 20th century knowledge, and as that was built on in the late 20th century, this is pulling that in. So this is our understanding of the physics of the atmosphere here. The blue cloud is the global temperature by about 100,000 runs of these long-term climate models if the people were turned on, which means if they're basically contributing greenhouse gases into the atmosphere. The green cloud is if you turn off the people, basically if you freeze the greenhouse gases where they were. And then the black line is what is observed. And so this isn't the only one, but this is kind of the sciencey one. We have no other explanation. We can't reproduce that black line of increased greenhouse temperatures without greenhouse gas contribution, right? So that's one of, I think we're going to do four here. So that's one, it's kind of the science and physics. The physics, we can't explain what's going on without the physics of greenhouse gases. This is the observational one. So even if we didn't understand the physics, this is the one that would be the smoking gun from an observational standpoint. And so what you're seeing on the left is the troposphere. So we used this platform earlier. So the troposphere is the lowest level of the atmosphere. It goes up, depending on where you are in the world, 30, 40,000 feet. It's where all the weather happens. It's where meteorologists learn about stuff. So it's the lowest part of the atmosphere. It's the part of the atmosphere that touches the surface. And it's about 30, 40,000 feet thick. And it's been warming, whether that's taken by weather balloons, by satellites, or by computer reanalysis of a lot of data. No matter how you look at it, it's been warming. The next layer up is the stratosphere. So when you fly on a cross-country flight, you'll poke into the stratosphere. It's 30, 40,000 feet above the ground, and it's been cooling. So whether you're measuring with weather balloons, whether you're measuring with satellites, or whether you're measuring with computer models, it's been cooling as well. You can't warm the bottom of the atmosphere and cool the top of the atmosphere without changing the composition of the atmosphere. This is the observational smoking gun. What greenhouse gases do is they trap heat from escaping near the surface. So you're heating the bottom of the atmosphere kind of at the expense of the top of the atmosphere. And this is kind of the observational proof of what's going on. If it were the sun, or if the warming were due to changes in our orbit, we'd be warming the whole planetary system. If the sun, if the sun had gotten brighter to heat us up, we'd be warming up everything. We wouldn't just be warming up the bottom of the atmosphere. Does that make sense? Okay. All right. So why does it matter? We'll go. So this is the relationship between climate and weather. So the things that you respond to, if they're not caused by the weather, the response is certainly affected by the weather. So here's kind of the climate relationship with weather. So we looked at this earlier. It's just a different graph of sea level rise. Sea levels are up about 3 inches since the early 1990s. And that's a nice scientific fact. But what that means, one of the things that means, and this is in the U.S., is if you live along the coast, particularly along the Gulf or the Atlantic coast, you're seeing a lot more nuisance flooding events. So clear sky, kind of onshore winds, high tide, ankle-deep water. That's happening a lot more in the U.S. And that is an economic nuisance in the U.S. But if you're a subsistence farmer in the Bay of Bengal on the coast of Bangladesh, that's salt water, and that's getting into your crops. So in the U.S., we have to deal with the consequences on our car's paint job or the sewage infrastructure in our city, and that's expensive and that's not trivial. If you're a Bangladeshi subsistence farmer, you have to decide where you're going to move your family. So the local consequences start to take shape in the face of this big global trend. So this is again U.S. based. So this is a glacier, Shepherd Glacier. This is one of the glaciers at Glacier National Park that's going away. And so this is 1911 versus about 15 or 12 years ago. It's going away. So, you know, you've probably heard all the glaciers in Glacier National Park are living on borrowed time, and that's true. And that's sad. We're losing kind of some cultural heritage there and some beauty and some nature. But if you're in South Asia, glaciers are what you time your crops on. So the melt that comes off of those glaciers every warm season is agricultural water and domestic water. And when you start messing with the timing and quantity of that water, you're messing with quality of life. And just like Bangladeshi subsistence farmers, Pakistani subsistence farmers aren't really driving the changes in the system. So there's a little bit of disconnect in what's driving the change and who's paying for it. About 1 billion people around the world rely on glacial water for domestic or agricultural use. Probably another example of, and I hesitate to say this was caused by climate change because that's a painstaking process, but maybe an example of the type of event that climate change will have us dealing with more in the future is Haiyan, a tropical cyclone in the Pacific in 2013. And so Haiyan was really unique in a lot of ways. So it was the strongest wind speeds ever achieved by a tropical cyclone. And there is almost certain evidence that as the globe warms, the hurricanes, typhoons, and tropical cyclones are all names for the same thing. So the hurricanes will be getting more intense. It reached intensity at the lowest latitude. It had record-setting intensity when it made landfall. So of all of the tropical cyclones in history, this one was the strongest when it hit land. And there was really extreme intensity overall in the basin. It also happened during a year, 2013, where the tropical Pacific was as warm as it had been since we've been keeping records, and sea level is up. And so what happened with Haiyan was this really bad, nasty storm hit the northern Philippines, where people are pretty much by default live in low-lying areas, don't have the resources to hop on a boat or a plane and get out of there, and we saw catastrophic losses in the Philippines. Northern Philippines, Filipinos aren't the ones driving the changes that we're seeing in the system. So this is, again, the Department of Defense, we work a lot with the military, and they talk about climate as a threat multiplier in vulnerable populations in parts of the world that they need to pay attention to, but it's also a multiplier of consequences in parts of the world that just don't have resources and suffer from regular weather events. All right. So this is some stuff with from the National Climate Assessment. This is hot off the presses. I honestly haven't digested a lot of this yet, but what they've done here, if you're curious, is they've broken down all of the different types of things that drive these fluctuations in the temperature. And so the sun hasn't been changing a whole lot. Volcanoes occur once in a while. They tend to cool when they do. Natural variability, which is largely that El Nino, La Nina, they all kind of cancel out. And basically the driving component is the atmospheric, the greenhouse gases. This is that same information on a different graphic. So we'll go through there. One consequence is that we've seen here, and this is something that we produce every 10 years with the USDA, is the hardiness zones, right? So where do you grow your bulb that you buy at Lowe's? Where can it grow? So this is the change in the past 10 years, basically the creep northward and upward of the hardiness zones. This is what's expected over the next 30 years. So hardiness zones should be migrating a few hundred miles north and a little bit up as well. That's for horticulture, but think about natural systems, crops, They're all sensitive to this. We're seeing Georgia is the peach state, right? So just a decade or two ago, South Carolina became the biggest producer of peaches as the peach crop kind of migrates northward, chasing the temperature profile that peaches need. Now we're seeing peaches showing up in apple country in western North Carolina where I live, and so it's really going on with crops. That's great. We're North Americans. We're actually well equipped to keep up with changes in cropping. Orchards are tough because you kind of have to plant and plan for 20, 30 years of productivity, but a lot of places in the world are seeing these hardiness zones related to their crops going away. They don't have the resources. They can't just switch from apples to peaches. It's tough. Okay, I'm going to cruise through these. These are all maps of the same kind of stuff, and frankly, it gets bleaker and bleaker as you go. So here's the precipitation change. We've seen a lot in the plains and the eastern U.S., a lot of increased precipitation over the year. That's a rule of thumb. I want to stop on this one. So one of the big things that we're going to be dealing with, and we're already dealing with, is the dosing of our rainfall. So like we said earlier, a warmer atmosphere can hold more water vapor. You can put more water vapor into a warmer atmosphere. And what that means is when the atmosphere is warmer and it's holding more water vapor, when a storm system causes that water to get precipitated out of the atmosphere, it can deliver a lot more rainfall to a spot. We're fueling the atmosphere with water vapor more. And so what this shows is, so there's two ways that very heavy precipitation is changing in the U.S. And it's particularly in the eastern U.S., east of the Rockies and particularly east of the Mississippi. It's changing in two ways. The big events are getting bigger, so the peak of like how much rain can fall in 24, 48 hours, we're seeing that increase, right? Both theoretically and observationally, we're seeing that increase. We're also seeing, and this what this map is getting to, is that our water budgets, the big events are responsible for more and more of our annual water budget. So if you, let's say here we get 25 inches of rain a year in Colorado Springs, right? That's our annual budget. In the mythical normal year, we get 25 inches here. And so what we're seeing over time is that 25 inches, and that 25 inches in most parts of the country is going up a little bit. But even if we held it, the events that are delivering that 25 inches are increasingly becoming fewer events that deliver a lot more rain at once with a lot more dry days in between. Does that make sense? And so this map shows some of it's one way to quantify that, but New England and the Northeast is getting 71% more of its rain now in these whopper events. That's what this is saying. So that has consequences here in the U.S. in like how do we deal with moving floodwaters and stormwater infrastructure. In a lot of the world, that means more flash floods. And I guarantee you can scour your newspaper as long as you want, and you're not going to find a lot of articles about flash floods ripping through a really nice part of town. We tend to put the less fortunate folks in any society right by the creek. And if you have emergency management experience, probably have seen this in your practice. So we're throwing a lot more water at folks in unregulated watersheds. Does that make sense? All right. Okay. This is basically showing the one sentence headline here is the wet places are tending to get wetter, the dry places are tending to get drier in the context of all of that. All right, so the last thing before a story is climate and extreme weather. And I hate to do this, but we're going to have to review some literature. It was written in the 70s by an author named Stallone, and it really perfectly describes the relationship between climate and big weather. And so here it is. This was I can't do this with the college kids. They're like, who are those guys? So this guy's weather and this guy's college, this guy's climate, right? Weather throws the punches, climate trains the boxer, right? We don't know what punch Rocky's going to throw with 2 minutes and 4 seconds left in the 7th round of his next fight, but we know that statistically, if we change the trainer to Mick, he's going to throw a lot more left hooks. He's going to throw some punches more often, and some punches less often, and some punches harder, and some punches less effective. Does that make sense? That's the relationship between extreme weather and climate. It's a coach, athlete, parent, student, teacher, student, parent, child. It's that kind of relationship. This kind of pervasive long-term influence, but not necessarily day-to-day direction. All right, let's go another one. All right, we'll go back in the 20th century even more. I have a 16-year-old boy, right? He's a 16-year-old boy, right? The house smells like feet all the time, just all the time, right? So he's kind of an impulsive guy, right? He acts quickly. He does, we're talking about extreme behavior here, so he can do that. He's got kind of he inherited from his old man kind of a short attention span, right? So he doesn't pay great attention to the long arc of things. He's in the moment. He's really sensitive to the world around him. He reacts to the things immediately around him. He can do extreme behavior if the right set of ingredients come together. We'll come back to that. The beautiful thing about him is he forgets quickly and moves on from these extreme events, right? And if we hadn't named him something differently, we would have named him weather. Right? That's weather. That's what weather is. That's extreme weather. You bring the right set of ingredients at the right time and something big's going to happen. And that's under a stable climate, right? So what happens if you change the climate? Here we go. Yeah, change the climate. Right? So what causes the extreme weather, the extreme behavior? Well, it's the same old stuff. He's still impulsive. He's still sensitive to things right around him. He's hanging out with his friends El Nino and La Nina for a few months at a time. They're kind of telling him what to do. But he seems to be getting into these extreme behavior situations more often. And that's because the ingredients that drive his extreme days, the ingredients that drive extreme weather, are the same as they used to be. It's just they're coming together more frequently or in different combinations or more often or at weirder times of year. And in this example, if you change the climate, this kid, the things that cause his bad days are the same things. He's hungry, he's tired, a girl was mean to him, somebody said something wrong to him, he woke up on the wrong side of the bed. All of those things are the same, but the trajectory of his life will have changed. It's where, and then this guy on the left gets blamed for everything, but you can't pin anything on him, right? That's parenting. He shouldn't have robbed that bank. That's bad parents. No, that's a really local thing. So climate and extreme weather is kind of the same thing. You have to look at the pattern of behavior over time. And very quickly, here's what is changing with climate and extreme weather. I think I'm running out of battery. Okay, so what we have here on the left is two bell curves. So this is the, like what I would describe with my colleagues as the statistical distribution of temperature outcomes. It's basically a bell curve where you basically drop a marble somewhere along that line each time the temperature is something, right? So just looking at the left bell curve, that is the climate that we knew in the late 20th century. So most of the events fall in the middle of the bell curve, and it tails off, and we have some rare extreme events, extreme cold and extreme warm over here. Does that make sense? That's what that left bell curve is showing. And so theoretically, if you were to warm the climate, if you were to move that bell curve to the right, to a warmer part of the world, you would see a few things happen. One of the stuff that we used to call extreme cold, we don't see that as much anymore. This is all theoretical, by the way. So one of the things is we would see much less extreme cold. The things that we used to call extreme warm in the pink, by moving that bell curve over, we're biting off a bigger chunk of that, right? We're seeing a lot more of what we used to call extreme warm. That's the theory anyway. And then if we move that bell curve to the right, we're basically biting off more unprecedented warm. So things that we never used to see, we start seeing rarely in the new climate. This is the theory, and the observations basically exactly back that up. So this graphic here on the upper left is the 50s, 60s, and 70s. Basically that same exercise of organizing them into a middle piece and some extreme pieces. And then we've preserved that trace with a green dotted line. And so this is the 70s, the 80s, the 90s, and the first few years of this century. So you can see that shift happening. And we're biting off more and more of these unprecedented warmth. So what are we seeing increasing? Big heat is up. Big cold is down, just like we would expect from that theory. Big rain is up. These are the three things that are crystal clear. We see it in the data. We're very confident in why it's happening. The kind of next category of things that we're seeing that maybe we're not seeing definitively or seeing everywhere, or we don't quite understand exactly what's going on, are the next ones. Big drought is up in most parts of the drought-prone world, but it's not quite as clean as we would have expected it. Part of that is due to this phenomenon where we get a lot more of our rain in singular big doses with a lot more dry days in between. That tends to be conducive to drought development. For hurricanes, if we were to get some colleagues of mine that study hurricanes and ask them, are we seeing more hurricanes? There would be a knife fight immediately. There would just be this awful, terrible argument with all of these big Latin words. It's just really gross. So we don't know whether, we are seeing more hurricanes, but we're pretty sure that that's because we're just better at seeing hurricanes than we used to be. However, there wouldn't be a fight about whether they're getting more intense. The intensity is up. So the average hurricane is getting a little more intense. We're seeing more hurricanes on the intense side. I haven't put it in this slide yet, but they're slowing down. So when they make landfall, they hover over a place longer. They're about 10% slower than they were in the late 20th century. Harvey is a great example of that. It's probably the extreme example of that. Just sat over southeast Texas for 5 days and made a lot of rain, a lot of inland flooding. And then with hurricanes, we are seeing, whether they're getting stronger, they are getting stronger, but even the ones that, today's Category 1 hurricane is working on an ocean that's 5 or 6 inches higher than it was in the middle of the 20th century. So Hurricane Sandy in New York, overtopped the Battery seawalls. It basically had a boost from climate change. The ocean was, helping it out by 4 or 5 inches, in addition to the sea surge of the storm surge of a few feet. Snow and ice, and there's not a clear signal on violent local weather and snow and ice. We haven't been able to make that connection. New York State, New York State. Okay, all right. This is just, I'm including this in case we want to share. We've talked about these. These are where you can go for vetted information by accountable people. Climate at a Glance can help you analyze trends in your region. So temperature, precipitation, and drought since 1895 at your county, down to the county level, but you can do state, or there's a few cities in there as well. Climate at a Glance. So this is the Louisiana state temperature in the summer. You can go get that data. You can download that data, put it in your spreadsheet, and do that. This is minimum temperature. So this is maximum temperature at Louisiana. Really noisy, not a lot of change. This is for summer since 1895. And this is minimum temperature, morning time temperature in Louisiana. Clear signal. So we're seeing, again, the warm times of day warming faster than the cold times of day warming faster than the warm times of day. We do the billion. We have an economist on our staff. I'm not kidding you. His name's Adam Smith. So he does the $1 billion disasters. We put these out every quarter as well. And then for the material, I want to spend 2 minutes telling a story. This is a story. It's going to use people who I'm familiar with, but the story's about you, and you'll see why. We've talked. It's been really bleak, right? Like, it's hard to be a climate scientist. It's changing, and it's causing people to suffer, and it's not going to get better, right? We can mitigate it. We can slow it down. We can work across generations to stop it. We're not putting Humpty Dumpty back together again. We're not going to be able to snap our fingers and miraculously come back to the climate in 1957. So you're on the front lines of dealing with the consequences of these changes, right? So I'm going to tell you a story that gets even bleaker. Hang with me through this story, okay? Because it's a rough first chapter. But the second and third chapter is about you, and it's beautiful. So let me tell this story. So I'm originally from Oklahoma. I grew up in Oklahoma. If you're from Oklahoma, all right. Yay. All right. You know about a chapter of our climate history. And so we had this thing called the Dust Bowl. It was a regional thing. It happened around here too. But based on where we were kind of in our development as a state, this was, a traumatic event. We lost a third of our population during this time. Third of our population, that's proportionally more than Syria has lost this decade. And granted, people in Syria aren't free to leave, but I mean, we lost a third of our population. It left a scar on our state's history. And it's the thing that happened, at least since the European settlement of Oklahoma. It's the thing that happened that frames a lot of our way of thinking. And we wrote novels about it. We wrote novels about the suffering of the time. We wrote songs about it. Woody wrote songs about the suffering of the time and the breakdowns in the relationships and all of the things that came with this Dust Bowl. And so this is a picture, and this is my grandmother, Vivian. And this is probably her little sister, Gladys. And this is probably their birth mom, Ludi. This is in Crowder, Oklahoma, down by McAllister, where they grew up. And so this is in good times. This is from the late 20s. And not too long after, if this is indeed Ludi, not too long after this picture was taken, things changed. The Dust Bowl started. The crops failed. The economy changed. And Ludi, like a lot of people in her situation, decided that permanent motherhood wasn't for her. And so my grandma became, at the age of about 12 or 13, the matriarch of the family. So her job, in the absence of having the mother around, was to drag Gladys around from house to house, neighbor to neighbor, uncle to aunt, friend of the family, and find a place to live for however long they could pull it off. And when she was dying in 2002, she shared a lot of her experiences in this, and it went about as well as you would expect a desperate 13 or 14-year-old girl dragging her little sister around a desperate part of the country to go. There were some bad men in her life, and it messed with her throughout her life. But her whole decade was spent trying to make sure that she and Gladys didn't get separated. I told you the first chapter sucked. I'm sorry. But this is not an unusual story. This is not unique in Kansas, Oklahoma, Arkansas. This happened to hundreds of thousands of families, right? This is a story in a lot of family histories. She was not unique by any means. But here's the part where you come in. So this is a graph of the drought signal in Oklahoma. And if you were to ask one of my colleagues to pick out what was the worst drought in your state's history that wrecked things, that caused these horrible losses of family and culture and life and society and drove a third of the population out, they would pick the 1950s. They would say, based on the data, looks like the 1950s is the one they wrote novels about and the one that made Woody write songs. And it's not the case. And this is where you come in, right? So this is the 50s drought signal in the part of Oklahoma that my grandmother was from. And this is the Dust Bowl. We took a harder punch in the 50s. And we didn't lose a third of the population. And we didn't lose all of our topsoil. And we didn't lose the fabric of our society. And the reason that happened was because a lot of things got better between the 30s and the 50s. The sons and daughters of the people that went through the Dust Bowl learned. And it wasn't science, actually. They learned practice, good works. So in science, we call good works good practice, right? So they learned good practice, topsoil management, water management, crop selection. Home economics was invented in the wake of the Dust Bowl. How to make a pound of flour go a little farther. All of that kind of stuff, right? And then we also had this incredible improvement for the difference between the haves and have-nots. You know, the 20s and the 30s weren't exactly this playground of family values, right? So we had institutions built up. We had faith in institutions built up. We had people working to educate and empower people in the field that were vulnerable. People like you. And I'm here to tell you, I wouldn't be standing up here spitting out big words and pretending I'm smart if it weren't for people like you working between the 30s and the 50s. People like you saved my family from a trajectory of ruin. And they saved hundreds of thousands of families from a trajectory of ruin. The work that you do, you may see wonderful results in the week that you're there. What you won't get to see, but I promise you, and I'm thanking you for people that haven't been born yet, is the generational good of what you do. Climate seems really scary right now. It is scary. It's a big issue. It's picking off our vulnerable people. The work that you do will show up in something like this someday. I promise you. And I'm thankful for the work that you do. Please keep it up. Do good works and do good practice. Thanks a lot for your time.
We're 5 minutes of Q&A. If folks have questions.
Yes, sir.
Derek, serious question. Have you shared your presentation with our president?
I don't rate that high. Oh, thanks.
You mentioned that the agriculture is like the second or third reason for climate change.
About third, I think, yeah.
A third. So
Yeah.
understanding agriculture in the United States, knowing that the United States agriculture is like the second export in the world, and that's where we found the low-income population surrounding the agricultural environment. So pushing environmental policies in the future that will regulate the agriculture infrastructure. Have we found initiatives to accommodate those issues in the future, where we don't push down more of those low-income populations?
So I'm going to dodge your question. I'm not anything close to an expert in labor policy. I can tell you from this experience, the ag economy changed massively. That was the thing that drove this exodus of people. The Dust Bowl was just an insult on top of it. It was the change in the labor dynamics, the mechanization of agriculture, and a lot of skilled workers finding themselves out of work, and the kind of tractorization of the ag economy. And I know a lot of the work in the 30s was repurposing and retraining and taking in a lot of those folks and empowering them. And frankly, fighting European fascism on the side. I mean, it's an amazing generation of people that were looking out for each other. So I'm sorry I don't have a well-informed response, but I know that we.
But pretty much dollar hit point, how much involvement in helping with the pages and what you're trying.
So I'm unfortunately, or not unfortunately, I'm in a science organization. If you were to talk with representatives and agencies that are smarter about labor policy, you'd get a better answer. I'm truly sorry that I can't provide a good, well-informed answer. Yes, sir.
With the disappearance of the glaciers and the warming of the Gulf and 5 inches more of sea level, is this really exponential? It isn't just, and scientifically, are you able to say with some certainty this is exponential and the next 20 years will probably be much worse than the last 20?
Yeah, it is increasing, so it's not linear. It is exponential. It's a gentle exponential. It's not a dramatic exponential. The big variables, the unknowns, the known unknowns right now are the collapse of ice sheets in Antarctica and to some extent Greenland. But Antarctica is where a lot of ice can crash into the oceans at once and can add a few inches to that global sea level within a few years. I mean, that's overnight geologically. It is, without that, even setting that aside, it is exponential. It's a gentle exponential. The rate is increasing slowly over time. And without these big events like Antarctic, they would expect to increase in that same trajectory. Is that fair?
I'm just curious, how often are organizations coming to you to retrieve this data for like grant writing, and has it, I mean, does it help in particular, grants to, for different things we're looking for, priorities we're looking for?
So people do use our information quite a bit. We typically, up until maybe 10 years ago, we worked with scientists that were researching the climate system. We are still catching up on both the business side of things and the NGO, nonprofit side on helping them get what they need. If you're writing a grant, that national climate assessment is a wonderful first entry. And then if you do need more specific, if it's a local grant, then shops like mine can help point you to that data. But the NCA, the National Climate Assessment, really lays out a lot of these topics and the resources really well.
So you have good outcomes on retrieving that data for grants, is what you're saying initially through.
Yeah, so we aren't involved in a lot of granting, but we are working with folks that are applying, yeah.
Okay.
Yes.
So do you have any kind of practical tips, like sort of slightly taking off your scientist hat and saying, if I had my wish, we would, we would do this?
Yeah.
And then secondly, can you just briefly say a little bit about the Climate Resiliency Toolkit?
Okay, yes. So there's two ways to approach climate change. One is mitigation, and that's usually some kind of communal, collective, political action to reduce the introduction of carbon dioxide into the atmosphere, which is almost always tied to some kind of fossil fuel energy policy. If you want to slow down climate change, that's the pathway. And there's a million ideas out there on how to do competing ideas, and a lot of noise. I think where we can make the most difference in the short term is on the adaptation side. So the hardening of our infrastructure, the triaging and tough decisions that come with who do we put or leave or remove from harm's way. And I talk about these waterways a lot. We saw that in a lot when I was working with emergency management in Oklahoma, where new arrivals to the state, typically Spanish-speaking, would live in mobile homes near a waterway, usually an urban waterway, and they lost a lot of kids in flash flooding. And I think working to help deal with today's climate in an adaptation way helps us deal with tomorrow's climate as well. I think in a general big picture, apologize for the lack of detail, helping people deal with today's climate is a really good foot forward in helping people deal with tomorrow's. And the Climate Resiliency Toolkit, if you look that up, that's basically a curated list of, and this would help with your granting question as well, of resources both. My shop deals with today and past. These also include projection information. It's one of our sister organizations in NOAA that puts this together. And so these are, I'd say, several dozen, up to about 100 curated. You kind of enter your topic. It'll recommend a tool or a set of tools, and you can go find kind of technical information. Is that fair? Okay, all right. Yes, sir.
Briefly, I guess, hearing what you've said, do you see an inflection point? One of the things that the story that's told between the 30s and the 50s is how resilient we are as the human race, right? The impact on climate, is there a point where we're unable to bounce back, where the degradation of the climate gets so bad and you're having folks move from coastal inland, and then you have inland waterways flooding, that it basically extreme weather overruns us? Do you see an inflection point, or will we always be resilient at an extreme cost, but always able to overcome climate?
So I'm not speaking for NOAA, the Department of Commerce, or the executive branch. I think there, and this is going to sound like it's a cute response, but I think the inflection point depends on who and where and when, really. So I think there are populations and people that are losing their way of life irreparably. The Pacific Islands, particularly in the South Pacific, Kiribati, a lot of the smaller atoll-based, they're going to have to move. I mean, it's over. The Native Alaskan populations here in our country, our fellow citizens, they're going to have to move inland. I think we see a lot in the Middle East. The climate didn't cause the Syrian situation, but the example we saw there is representative of what a lot of the big geostrategic planners worry about, in that you had a pretty horrible governmental regime in Syria that was oppressive, and you had a lot of unhappy young men in eastern Syria in a very agricultural part of the country, and then there was the warmest 2-year stretch that they've had. Turkey shuts off the Euphrates River to keep the water on their side of the border, and you have essentially a farmers' rebellion morph into what was bound to happen anyway, this powder keg, religiously informed, large-scale rebellion, and then all of the trauma that happened after that. And I think, and I hope it's okay, I hope it doesn't sound too cute, but I think there are inflection points depending on who and where. I think it's a case-by-case basis. I mean, we're pretty well equipped in North America to handle a lot of this, but most of the world isn't nearly as well equipped as us. Thank you. Thank you. Appreciate it.
All right, bear with me for a few announcements, and then we'll also announce the revised start time for our next sessions. What an amazing presentation. I know some of you got to see that last year in Asheville, but for such a complex and technical topic, I know it was certainly helpful to see it again, and I think our newcomers probably felt the same way to see it the first time. So thanks again, Deke. As you all know, if you haven't had a chance to ever check out Laudato Si, the encyclical, please do that. Deke mentioned several issues related to justice and equity and ethics that Pope Francis expands on in a pretty powerful way. So please do check that out. April Wood will be here at 4:30, from 4:30 to 6, our speaker last night, who showcased that pretty powerful and robust analytics tool. Feel free to spend some one-on-one time with her or as part of your teams to learn more about it or ask your questions, provide feedback, and that'll be in Pikes Peak 3 from 4:30 to 6. Kim Burgo also will be facilitating a community of practice with Gina Whiteman from 4:45 to 5:45, and I believe that is in the Gold Camp room. And I only bring that up because it's an off the main path session. So if you were signed up for that, double check and make sure you don't miss it. That's at 4:45. Dinner will be here at 6:15. A movie will follow. We will flip the room, but it is movie night, and I've had a few folks ask. The movie is optional. We'd love to have you here, but no one is taking attendance at the movie. So it is free time, but a lot of folks will be gathering up here for a chance to share some popcorn and a film. We did find a cell phone. It was delivered to us. I don't think it's been picked up. It may have. Long story short, if you're missing a cell phone, we have it in the staff office. Just ask any one of us with a staff flare on our tag, and we'll help you out. I believe we have one more announcement here. Oh, yeah, don't forget, if you're still looking for your chance to be the next Catholic Charities Network star, during the breaks, we have the film session going. Give us your best bit in response to the questions that Sheena will have for you. And I think that's all we have by way of announcements. The next sessions, I believe it's about 3 o'clock right now. Let's go ahead and take 10 minutes to go ahead to get to our next sessions. We'll flip the rooms, make sure all the presenters feel comfortable. And then, hold on just a moment. So those are scheduled to go until 4:30, and then there is a little break there for some folks. So simply presenters, take as much time as you would normally need for your folks to get maximum engagement out of your session, but be respectful of the time, okay? Thank you so much.